This led Einstein to develop his special theory of relativity, which gives V equals V1 plus V2, just like the old formula. But there is a correction. Düzeltme. Here is the relativistic correction. Divide by 1 plus V1 V2 over C square. Now this is a more general result. It applies under general conditions. It applies under situations where there is light involved or something is moving close to the speed of light. Now we can do many experiments, for example at CERN and other accelerators with particles that are moving not exactly but 80% of the speed of light, and for them we can test that this is true. Okay? Now let us see what this will give us in the case of the light traveling inside the train. In that case, light emitted in train. So V1, the velocity of the thing that's moving in the train, is c. Okay? Let's see what the formula will give. Then C prime is simply, for V1 I'm going to put C plus V1 divided by 1 plus V, I'm sorry, this is V2. V2 is the train's velocity. Okay? 10 kilometers per hour, let's say. Here I have V2 C over C square. Right? Let's continue the calculation. Is everybody with me? So, electricity and mechanics problem, Einstein now tries to make a more general theory. And in this theory, he thinks about how time is measured, how distance is measured, how velocity is measured, etc. And this is the new formula. So, C cancels here. And this result, if you continue the algebra, you will find that this is just C. It's a simple formula, not as simple as the old one. But it's not just any simple formula. Einstein deduced it on the basis of making these two different experiments agree, compatible. Okay? So this now gives this a way of adding velocities of things with respect to train, with respect to platform, station, that has the property that if one of the objects is light, its velocity is the same. So it's beautiful. It explains that everything is alright with the equations for light waves propagating, because no matter who measures the light waves, they will get the same velocity, and that formula gives the right result. Now, of course, you could think of other formulas that give you the right result. Okay? But to test if this one is the correct one, they do more experiments, and it is the correct one. Next question is, well, then what's going to happen to Galileo and Newton? Is everything they did, and all of the classical mechanics, which we are still using to design our cars and trains and airplanes and everything, is that wrong? So the next requirement from this new theory is, in appropriate conditions, it should give back the old theory. What are the conditions of the old physics? That trains and guys running in trains and everything else, all those velocities are small compared to the speed of light. So let's now see that. Here slow must mean slow with respect to the reference in this problem, which is the speed of light. So it means, slow means V1 is much less than C. V2 is also much less than C. Okay? For example, V1 is 1% of C and V2 is 1 over 1,000 of C. Then what we have is V is equal to V1 plus V2, 1 plus, well, let me just write here. Okay. A very small number. Right? So it is not exactly equal to V1 plus V2, but it's approximately equal to V1 plus V2. The old theory, classical mechanics, is approximately true when V1 and V2 are small compared to C. So what happened when it became possible, both with theoretical advances, the understanding that electricity and magnetism gives light, and with the possibility of making experiments to test these things, to measure such very high velocities, you need very fine clocks and everything else. Two theories are incompatible, then science makes a generalization. Such generalizations are very rare. I mean, small changes in conditions are addressed by scientists all the time, but something like relativity, the big paradox between two areas of science, takes somebody like Einstein. Okay, it doesn't happen very often that such a big change takes place. And then what happened to the old theory now? It is not wrong, but it's approximate. The new theory is now more complete. That means it's valid under a wide range of conditions. But even that, as Einstein soon realized, his special theory of relativity was not a completely general enough theory, because it only gives correct results for things that move at constant speeds. If you want to include things that accelerate, like something falling down, gravity, then Einstein himself realized that this special theory is not enough. He must do something even more general to take account of both gravity and acceleration and things moving at speeds like the speed of light. And then, about 10 years after the special theory of relativity, he developed the general theory of relativity, which is more general. So special theory is again not wrong, but it is not general enough. And the general theory is passing new experimental tests, still going on, but it's now quite solid. But we are not sure that it's absolutely general. In the conditions of present experiments, it's valid. Okay? Okay, so we have had a bit of discussion of relativity and what is theory and so on. You can start by just going into Sukkot, playing around, reading the first few chapters there. Okay, on Wednesday we'll meet again. Okay. If you have any questions, come to me.
Normalde bir şekilde ışık hızını basalım, buna yakınlığını